Section: Introduction. In this section, we discuss the importance of reasoning in large language models, LLMs, and how it enhances their performance across various tasks. We highlight that many methods have been developed to improve reasoning, with chain of thought, COT, being the most prominent. COT helps the model provide more reliable answers by prompting it to think step by step, breaking down problems into manageable parts before reaching a final solution. We illustrate this with examples showing that without COT, the LLM often gives incorrect answers. However, when using COT, the model systematically addresses each step, leading to the correct answer. Despite the benefits of COT, it significantly increases the number of tokens used, which can lead to higher costs in terms of computation and time. This raises the question of whether the reasoning process is too lengthy and how we can make it more efficient. We demonstrate that LLMs can adhere to a token limit in prompts. By incorporating a token budget, we can effectively reduce the number of tokens used in COT reasoning. Our findings show that a reasonable token budget can cut down the token cost significantly while still allowing the model to arrive at the correct answer. However, if the budget is set too low, the model tends to exceed it, which we refer to as token elasticity. To tackle this issue, we propose a method called TAIL, Token Budget Aware LLM Reasoning, which dynamically adjusts the token budget based on the complexity of the problem. TAIL estimates an appropriate budget for each task and guides the reasoning process accordingly. We present various implementations of TAIL and share experimental results indicating that it can greatly reduce token costs while maintaining accuracy. In the related work section, we review advancements in LLM reasoning techniques that generate intermediate steps for improved performance. We note that while these methods enhance accuracy, they often lead to increased token usage, which poses efficiency challenges. We also mention other approaches aimed at reducing token consumption, but many are limited in their applicability to LLMs or impact reasoning accuracy negatively. Section Summary. In this section, we discuss the importance of reasoning in large language models, LLMs, and highlight the chain of thought, COT, approach, which improves accuracy by breaking problems into intermediate steps. We introduce our method, TAIL, Token Budget Aware LLM Reasoning, which optimizes token usage during COT reasoning by dynamically adjusting the token budget, achieving an average reduction of 68.64% in token costs while maintaining high accuracy. Section: Token Redundancy in LLM Reasoning. In this section, we explore token redundancy in large language model, LLM, reasoning and how to find the optimal token budget for specific questions. We notice that different token budgets yield varying results, prompting us to ask how to effectively search for the best token budget for a given question and LLM. To find the minimal token budget necessary for accurate responses, we employ a binary search algorithm. Initially, we use a standard chain of thought, COT, approach to generate an answer for each question, which helps us determine the maximum number of tokens needed, referred to as the right boundary. We then check if a budget is feasible, meaning it allows the COT prompt to maintain the correctness of the answer. Our binary search starts with 0 as the left boundary and calculates the midpoint between 0 and the right boundary as the current budget. We keep track of previously searched budgets and continue adjusting our search range until we find the minimal budget that still produces a correct answer. However, we realize that the smallest budget does not always equate to the optimal budget. When the budget is too low, the actual token cost can be higher than when a larger budget is used. During our search, we observe a phenomenon we call token elasticity. As we approach the minimal budget, we find that reducing the budget too much can lead to increased token costs. This is illustrated in our figures, where we see that as we decrease the budget, the token costs begin to rise after a certain point. To address this, we enhance our binary search by adding a greedy search strategy that seeks to minimize token costs while ensuring the correctness of the answers. We modify our feasibility check to include a requirement that the new budget must lower the token cost compared to previous budgets. Based on our findings, we developed a method called TAIL, which focuses on token budget-aware reasoning in LLMs. TAIL aims to create prompts that maintain performance similar to standard COT while reducing token costs. It follows a two-phase approach, estimating a reasonable token budget and constructing a prompt based on that budget. Our observations indicate that only budgets within a reasonable range can effectively balance token costs and LLM performance. Ultimately, TAIL estimates a suitable token budget and uses it to generate the final answer, as shown in our workflow example. Section Summary. In this section, we explore the concept of token redundancy in large language models, LLMs, and propose a method, TAIL, for optimizing token budgets to enhance reasoning efficiency. We demonstrate that while a minimal token budget can maintain answer correctness, it may not minimize token costs, leading us to develop a two-phase approach that balances budget estimation and prompt construction for improved performance. Section: Budget Estimation. In this section, we explore how to estimate a suitable budget within a reasonable range by considering two main approaches, a zero-shot mechanism and budget regression. We also discuss how we can enhance budget awareness in large language models, LLMs, through fine-tuning. Our goal is to create an estimator that accurately predicts the optimal budget. For the zero-shot estimator, we utilize the reasoning capabilities of the LLM itself. Before we ask the LLM a question, we first prompt it to estimate the number of output tokens needed to respond. This approach is based on human-like reasoning. Just as people can quickly gauge the time needed to solve different types of math problems, the LLM can provide a budget estimate after a brief review of the question. Our evaluation shows that many of the estimated budgets are close to the optimal budget we searched for, demonstrating competitive performance. In the regression estimator, we aim to train another LLM to estimate the optimal token budget for a specific question. We use a dataset that includes instruction prompts, questions, and the optimal budgets we found through our search algorithms. We initialize our model with a pre-trained LLM and create target outputs based on the optimal budgets. Our objective is to minimize the difference between the model's output and the target output, optimizing the model parameters to improve accuracy. To instill token budget awareness in the LLM, we fine-tune it to incorporate budget estimation into its reasoning process. This involves two main stages: generating target outputs and fine-tuning the LLM. In the first stage, we prompt the LLM with a chain-of-thought prompt that includes the optimal token budget, guiding it to produce outputs that adhere to this budget. In the second stage, we fine-tune the LLM using these crafted outputs, encouraging it to internalize the budget constraint and favor concise reasoning. This two-step process helps ensure that the LLM generates responses that are both accurate and token efficient. Section Summary. In this section, we explore budget estimation methods for large language models, LLMs, focusing on a zero-shot estimator that prompts the LLM to predict output token needs, and a regression estimator that fine-tunes another LLM to estimate optimal budgets based on specific questions. Additionally, we discuss how we internalize budget awareness in LLMs through a two-stage fine-tuning process, enabling them to generate concise and efficient responses while adhering to token constraints. Section: Evaluation. In this section, we present the initial results of our zero-shot estimator method, TAIL. This project is still in progress, and we will provide more updates soon. We conducted experiments using three advanced language models: GPT-4o, GPT-4o Mini, and Yi Lightning. Our evaluation focuses on three main research questions. 1. How well does TAIL reduce token costs while keeping LLM performance intact? 2. How effectively does TAIL estimate the token budget for a given question? 3. How adaptable is TAIL across different leading LLMs? For our experiment setup, we aim to balance LLM performance with the costs of extra tokens. Specifically, we want to minimize token usage while ensuring the LLM performs comparably. We evaluated performance using three challenging math datasets: GSM-8K, GSM-8K0, and MathBench. GSM-8K0 is particularly designed to analyze over-reasoning and redundancy in LLM outputs, embedding answers within the questions to simplify responses. We measure accuracy by checking how many answers generated by the model match the correct answers in the dataset. We also assess the number of output tokens by calculating the average tokens used for each task. The more output tokens generated, the higher the costs incurred. In our findings, we compare TAIL with other prompt engineering methods, such as directly answering and vanilla code, across 7 datasets. TAIL shows significant improvements in efficiency while maintaining competitive accuracy. While directly answering has the lowest output tokens and expenses, it also has the lowest accuracy. Conversely, vanilla code achieves the highest accuracy but at a high token cost. TAIL strikes a balance, achieving competitive accuracy while significantly reducing token costs and expenses. For instance, on the GSM-8K dataset, TAIL improves accuracy to 84.46%, surpassing vanilla code. On GSM-8K0, it reduces output token costs dramatically while maintaining high accuracy. Additionally, TAIL shows cost-effectiveness by lowering expenses significantly on math bench arithmetic while achieving reasonable accuracy. Overall, TAIL demonstrates that being aware of token budgets can lead to substantial reductions in costs without sacrificing accuracy, making it a more efficient choice for budget-limited reasoning tasks. These results indicate TAIL's adaptability across various tasks, showcasing its potential for real-world applications while effectively managing resources. Section Summary. In this section, we present preliminary results for our zero-shot estimator method, TAIL, which shows significant improvements in efficiency and cost-effectiveness across 3 state-of-the-art LLMs. TAIL reduces output token costs by an average of 68.64% while maintaining competitive accuracy, demonstrating its ability to optimize reasoning tasks without compromising performance. Section RQ2. Effectiveness of budget estimation. In this section, we evaluate how effective our budget estimation is. An ideal budget estimate should be close to the best possible budget and fall within a specific area we define as the ideal budget range. We assess this using 2 main metrics, in-range accuracy and out-of-range distance. In-range accuracy tells us if our predicted budget is within the ideal range, while out-of-range distance measures how far off the predicted budget is if it falls outside this range. A higher in-range accuracy and a lower out-of-range distance indicate a better estimate. Our evaluation shows that we have an in-range accuracy of 60.61%, meaning over 2/3 of our estimated budgets are in the ideal range, with an average offset of 109.64 tokens for those that are not. Next, we look at the generalization of TAIL. Our results demonstrate that TAIL effectively reduces output tokens and costs while maintaining competitive accuracy across different models like Yi Lightning, GPT-4o Mini, and GPT-4o on Math Bench College. We achieve significant token savings, cutting output tokens by 62.6% for Yi Lightning, 61.5% for GPT-4o Mini, and 69.8% for GPT-4o compared to vanilla code. We also see notable expense reductions, with costs dropping significantly for each model. Despite these savings, TAIL maintains strong accuracy, with scores comparable to vanilla code. However, we notice the most significant accuracy drop for GPT-4o Mini, likely due to its smaller number of parameters, which makes it harder to provide correct answers within a limited reasoning length.